Okay, well, good morning, everyone. Like Melissa just said, I'm a climate system modeler here within the Centre of Excellence. Some of you may be aware that today actually is the winter solstice. So happy solstice, everyone. In some parts of the world, people like to celebrate the solstice by disrobing and jumping into the ocean. We're going to do something a little bit more sedate this morning. We're going to mark the solstice with a lecture on coupled climate system modelling. It's a strictly clothes-on lecture. So, like Melissa said, you've heard a lot of talks this week about all the individual components of the system, the atmosphere, the ocean, some weird bits like the land surface. But what I'm going to talk about today is bringing them all together and seeing how much fun we can have with coupled modelling. So, just start with some quick basic concepts and motivations. So basically the what and the why questions. What's a coupled model and why do we care? In reviewing the literature, I actually struggled to find any standard definition of what a coupled model actually is. So what I'm going to do is use my own personal definition here. So a coupled climate system model is one that A, describes multiple components of the climate system, but most importantly of all, B, actually describes the interactions between them. Why do we care? Well, basically, this is the Earth. Welcome to your home. This is where you all live. The Earth is a coupled system. The Earth is a very tightly coupled system. Like I've said, you've had talks this morning about, or this week about all the various components of the system, the ocean, the atmosphere, the land surface. All these have behaviours of their own. All these can be and are modelled by themselves. But most of the interesting behaviour within the climate system comes from the way these components actually interact with each other. So why do we need coupled models? Well, there's a range of reasons. First of all, and perhaps most commonly, we want to actually be able to predict possible future states of the climate system for reasons maybe of short-term forecasting or climate change adaptation or mitigation. Perhaps we want to try and understand past changes within the climate system. We might want to detect and attribute human influences. We may want to explore properties of the climate system. But above all, we want to answer questions. And those questions vary depending upon what our scientific motivations are. But generally, we want to ask a question that might range from being a science question, perhaps, like how does it work, or a policy question, for example, why does it matter to us? Now, there's only one Earth, and we can't or really shouldn't perform experiments on that. And that Earth is much too large and much too complex to be simulated within a laboratory. So really, numerical models are the only way we can actually properly address these questions. And most of the things we care about within the climate system are actually coupled phenomena. So coupled models are what we actually need if you want to answer all these questions. So a few examples of the sort of questions we might want to answer. First of all, standard future climate change projections. This figure is one I'm sure you've all seen before. It's from the last IPCC report. This is from the fourth assessment report. A few years old now, but the fifth one's not quite out. So for the time being, the fourth assessment report is still state of the art. And this just shows evolution of the global mean surface air temperature, in this case, for a range of climate scenarios right through to the year 2300. Now, of course, the response of the climate system, and particularly the very lagged response, whereby the fact that the warming continues for centuries into the future, is of course a consequence of the heat capacity of the ocean. So, even something as simple as global warming is very definitely a coupled phenomenon. The global carbon cycle, of course, very important in terms of being able to model future evolution of greenhouse gases within the atmosphere. And the global carbon cycle is in fact an extremely coupled phenomenon, as it is involving not just in fact components of the human system, because of course you have human emissions are part of the equation these days, but also of course it involves the atmosphere, the biosphere, the land surface, the ocean, and in fact biogeochemical cycles within the ocean. So really, if you actually want to be able to predict how greenhouse gases might evolve during the 21st century, that is, in many ways, actually the ultimate coupled problem, and this is sort of still the holy grail at the moment as far as coupled models are concerned. Another example, of course, we're not just interested in like change over time or trends, we also care about variability within the system as well. And of course, the classic example there, the largest source of interannual variability within the climate system is ENSO, El Niño-Southern Oscillation, and this in fact is also a very tightly coupled phenomenon. It's a chaotic phenomenon, but arises spontaneously from within the coupled atmosphere-ocean system within the tropical Pacific. So again, if you want to actually predict ENSO or predict how, either for reasons of seasonal forecasting or maybe to predict how ENSO might evolve under global warming, again, this is a coupled phenomenon. Coupled models are the only way of doing this. And last but not least, some slightly weird people like me actually care about the past and find the past quite exciting. So this shows a whole range of reconstructions, in this case, of how northern hemisphere temperature has evolved over the last 1,200 years. Quite a lot of scatter there between the individual reconstructions, but they basically tell a consistent story. It was warmer during the first part of the last millennium. This is a period called the medieval climate anomaly. It cooled down through to a little ice age here, and then warmed up again, of course, during the industrial period during the 19th and 20th centuries. Superimposed on that is lots of decadal tercentennial scale variability. Now, this is actually very important, both from the point of validating models, but also from the point of actually providing information about what drives the climate system, because if we can actually understand what it is that caused all these changes and what drove all these changes within the system, then that gives us the understanding of the Earth system that we might actually need to be able to predict the future. So that's the what and the why. Hopefully you're sold by now on the importance of coupled climate system modelling, and now you'll want to go away and build one. So let's go on with the how question of how we actually go about doing that. Well, first of all, quick sort of basic modelling concept. There's no such thing as a universal coupled climate system model. There are many different sorts of models that could all be classified as coupled climate system models. And they're categorized, depending on the particular paradigm you subscribe to, as being either a spectrum of complexity or a pyramid of complexity. But what those two paradigms have in common is they both see models in terms of degree of complexity. And there's really two different ways here we can define complexity. The first way is the number of different components described, or the number of different phenomena described by your model. And the second aspect is simply spatial resolution. So you can have anything from a simple box model right through to a high resolution coupled climate model, and your model might describe just two phenomena like the atmosphere and ocean. It might try and incorporate other phenomena such as the carbon cycle. So bearing that in mind, now you want to go away and design your own coupled climate system model. First thing to remember is it's a tool. All models are tools. So the type of model that you use depends upon the type of question that you want to answer. So before you even start, you have to ask yourself a lot of questions and determine what the answers are. So for your question, which components of the climate system do you need to model? If you want to model ENSO, atmosphere, oceans, fine. If you want to model the global carbon cycle, you've got to start bringing in biogeochemistry, vegetation, land surface, and a whole lot more. What processes do you need to model to simulate your phenomenon? Which quantities do you need to model? Which information do you actually need? And again, what sort of model do you need? Is a regional model enough? If you're interested in ENSO, then a regional model of the tropical Pacific might potentially be enough. For many problems, you might need a global model. How much spatial resolution do you need? Again, basically the more the merrier, really. I mean, as a general rule, the higher the resolution, the more realistic your climate simulation will be. But of course, the downside is computational cost increases very rapidly with resolution. Last but not least, how long do you need to run your model for? For the sort of problems I like to work on, which is paleoclimate, I typically want to run a model for anything from 1,000 right through to 10,000 years. But if you care about 21st century climate change, 50 to 100 years is probably enough. And of course, the most important point is these questions are very highly interrelated. For example, an all-singing, all-dancing, high-resolution global climate model is going to be much too computationally expensive to make it feasible to run it for 10,000 years. So model choices always involve a certain degree of compromise. And the most important thing to remember, of course, as well, so maybe you don't go home disappointed at the end of the day, is that no model is a perfect representation of the real world. I mean, ideally, the more processes you have, the higher the resolution, the more realistic it will be, but no model is perfect. So, now you've made your design choices, let's start actually building the model. So, traditionally, once upon a time, when coupled modelling first began, you basically just sat down and wrote your own computer program from scratch. Slow, tedious, but there was no alternative. Fortunately, these days, there are much more enlightened ways of going about things. How you build a model in the modern world is you generally would take existing components that are pre-developed by other groups, you combine them together in whatever the optimal way is for you, and bingo, you have your model. Well, not so simple, of course. Once you've actually done the programming work, you have to test your model, you have to debug it, and then most important of all, you actually have to go in and sort of tune your model and determine the optimal settings of the parameters so your model actually is as realistic as possible. And most important, of course, and sometimes underappreciated, is evaluation. It's critically important before you use a model for anything. So evaluate. Don't go away and run your model for the 21st century without having checked if you get the present day climate right. Now, as you're probably gathering, this is a very specialised and time-consuming process. A typical modern state-of-the-art coupled climate system model would represent an investment equivalent to at least hundreds of person-years of work, and what you would be left with would be an extremely large and complex piece of software. I always like to try and visualise things. You really get your head around things when you can visualise them. So what I brought with me, the first prop of the day. Now, the model I work with personally, CSRO Mark III, I would say it's a reduced resolution, quite a simple model by modern standards. But even that model is 90,000 lines of source code. So I actually thought I'd bring those 90,000 lines with me. So there you go, 4 pages to a page. That would have been state of the art about 10 years ago. That's what a model looks like. That's a simple model. I might actually pass that around in case anyone actually feels inspired. There's no test later, it's all right. But a case study. So you probably heard about Access at some point during the week, I'm sure. This is the new climate system model for Australia. So Access stands for Australian Community Climate and Earth System Simulator. Now, like I said, modern model development, you don't reinvent the wheel, you don't start from scratch, you take pre-existing components and bolt them together. So the basic physical core of Access consists of atmosphere model from the UK, ocean model from the US, sea ice model also from the US, and the one homegrown thing is the cable land surface model, which I'm sure you've heard about from Australia. And to actually bolt all those together and get them all talking to each other, we need this thing called a coupler, and the coupler comes from France. So it's a very international model. Last time I checked, it was running at about 1 million lines of source code, which is about 11 times longer than what you've got there. Quite computationally expensive at the standard resolution. You can do about 2 to 3 years per day, and every year of the model you run generates about 50 gigabytes of data. So yeah, running a state-of-the-art model is a pretty serious undertaking. It's illustrated by, I just downloaded this last night. This is from the Corker, so Centre for Australian Weather and Climate Research website, and this is the current Earth system modelling team within Corker. Unfortunately, you probably can't quite read that. Now, not every single one of those people was working on Access, but most of them are. And you see that there's quite a few names on the screen there. So building models in the present day is not something the small team of 2 or 3 people do. It's something that a very large number of people, all with distinct specialisations of their own, do. And in fact, based on the science plan for Access, this is basically what it will look like when it's eventually finished and all the extra bells and whistles have been added on. So in the centre, you've got the most important components of any modern coupled climate system modelling. This is the coupler. This is how all those individual components actually talk to each other. And that handles the communication between all the different components of the model. So you have your atmosphere model from the UK, your Australian land surface model, your American your ocean model, your American sea ice model, and various sort of chemical and biological components that will be added in eventually. So yeah, building a model in the model world is very much a case of take your components and bolt them together, which may remind you of a certain famous toy from Denmark. It's subtitle for my talk, Coupled Climate System Modelling Lego for Adults. Because it does feel like that sometimes, really. It's basically take a lot of components, stick them together, and there's your Earth. So this is Coupled Climate System Modelling in one image. He says we can't have fun. Now, okay, so let's go into a bit more depth in terms of some of the challenges actually involved in doing this and some of the solutions, so how we actually fix those. So coupling is not quite as simple as it might sound, of course. First of all, you have to develop interfaces for each component of your model. I mean, just because you have an ocean model and just because you have an atmosphere model does not mean they can set up individually to like pass out the fields that the other model needs. So a solution to that is generally as part of coupling, you would have to make some changes to the individual components before you couple them, just to make sure that as they run, they're kind of passing out and expecting to receive back the various fields you want to exchange between your models. And don't worry, I will give examples of all this over the coming slides. The next problem, of course, is the components generally use different spatial grids. Ocean models, for example, are generally higher resolution than atmosphere models, and the coastlines generally aren't in the same places. So somehow you've got to deal with like passing a heat flux from an atmosphere to an ocean when they're on a different grid, with all the grid points in different places, and the surface of the ocean doesn't even quite line up between the two models. So you use spatial regridding techniques to handle the exchange of the fields between the component models. But of course, the real trick there along the way is to actually make sure that basic physical quantities such as energy and mass are conserved as you do this. Another issue is components use different time steps. Atmosphere models generally use quite short time steps, maybe 10 minutes as they step forward in time. Ocean models might use something more like an hour. Land surface models can be even longer. So somehow you've got to deal with communicating between models where the atmosphere model steps forward 10 minutes at a time and your ocean model steps forward 1 hour at a time. Once you've coupled them in the course, errors in the climatology will inevitably arise. No model is perfect, which translates as all models are wrong, or all models will exhibit errors. But at least by tuning your model during the development process, you can improve the agreement with observations. And last but not least, and very important, is actually drift. So the sort of feedback loops you actually want to represent within the climate system of how the state of one system influences another is actually a blessing and a curse, because if your model has an error, those same feedback loops you actually want to capture for physical reasons will actually cause errors to amplify and propagate within your model. So let's say, for example, many ocean models are too cool in the Eastern Pacific. Now, if you're running your ocean model by itself, it's a bit too cool, that's the end of the story. You couple it to an atmosphere model, and of course your ocean model is a bit too cool. Well, now suddenly the atmosphere cools down as well, so the heat flux into the ocean changes, so the ocean cools down a bit more, and so on and so forth. And this is actually a big problem within models, is that the model actually can systematically drift away from its initial state over time. Tricky one to fix, but tuning, of course, can help here. So, an example, atmosphere-ocean coupling. These show the fluxes that are exchanged between the atmosphere and the ocean within a typical climate system model, as well as in the real world, of course. And that's quite a few. They basically exchange mass in the form of water, perhaps gases, perhaps salt. They exchange energy in terms of the various components of the surface energy balance, so the atmosphere and the ocean exchange radiation, latent heat, sensible heat, and they also exchange momentum in the form of wind stress. So all these fields are exchanged between these two components. So when I was saying just now about you have to configure the models with an appropriate interface, you actually have to make sure that your atmospheric component and your ocean component within your coupled model actually are expecting to exchange these two fields. And only when you've done that can you actually couple them properly. I mentioned the spatial regridding issue. Fortunately, modern couplers like Oasis handle this quite seamlessly for you. You basically can just feed in a whole series of spatial fields in Model A, and actually Oasis will do the various remapping and conservation issues for you and pass those fields out to Model B. So in the modern world, actually, this is quite a straightforward issue, at least in theory. Time management. Again, this is actually from the access coupled model. You have the issue that your ocean model and your atmosphere model have different time steps. So as we go from left to right here along this slide, we're moving forwards in time. And again, the coupler here actually basically does the work for you of grabbing a field from one model, passing it back to another, and over time it deals with the fact that one model, for example, might have a longer time step than the other, so it actually deals with the various averaging or interpolation issues in time that you have to deal with to actually get your models talking seamlessly to each other. So I mentioned evaluation, of course. This is the most critical part of model development. You have to evaluate your model to make sure it agrees sufficiently well with observations before you can go away to use it to do all the really cool science that you want to do. So this is a figure from the last IPCC report. This is from the AR4 report. So one of those panels shows the observed annual mean rainfall. The other panel shows the mean for all the different models that were in the AR4 report. Anyone like to try and guess which one's which? Yeah. Yeah, you can tell actually, because it's just slightly higher resolution than the bottom panel. Oops. And also the model fields are excessively zonal, which is a bias that many models have. But it's not immediately obvious. It doesn't like jump out at you straight away. So models are actually pretty good, and models actually do agree with observations pretty well, certainly in terms of the larger scale fields. After you check for the present day, you might want to run your models for the past, because running models for the past is the only way you can actually evaluate the ability of your models to simulate transitions or changes over time. So this is from a paper that came out just this year. Again, I showed you those reconstructions at the start of Northern Hemisphere temperature over the last 1200 years. The grey shading in the background is the mean and uncertainty range from all those reconstructions. And the coloured lines now are a whole range of different model simulations. And this shows the ability of the models to actually capture these changes. And certainly in terms of the 20th century warming, or in terms of the interdecadal variations, the models are doing pretty well. Not doing quite so well at capturing the long-term cooling trend from the medieval climate anomaly through to the Little Ice Age. And there's a whole range of reasons why that might be true, and it may even be the data that's wrong, not the models. But at least it shows the models have some skill that they can capture. For example, over the second half of the millennium, the models are actually in very good agreement with the data, actually. So the models can simulate changes and, decadal variability within the system, as well as getting the present-day climate right. Now, you can't really use future climate to evaluate your model without a time machine, but someone did do something quite cool just within the last few weeks, actually. Someone took a set of climate projections from 1996 and checked 16 years later how well they've done. So the dotted line here is the mean of a batch of model simulations that was run in 1996. So about here is when they were actually run. The red line shows observations, both historical up to that point and what at that point was the future evolution of the climate system afterwards. Yeah, actually, they're pretty much on top of each other. They agree almost perfectly. So this is probably the first example of someone actually evaluating their model by simply sitting and waiting for a very long time. Involves a certain degree of patience, but it was actually worth it because they were rather heavily vindicated in terms of their model. We care about interannual variability as well as trends. So here's a model evaluation. Again, this is for all the models that went into the fourth assessment report. And this is the power spectrum. So here's periods along the bottom, power along the y-axis. So these thick black, either solid or dashed lines, are a variety of observed data sets, and the coloured lines are individual models. Now, you can sort of see that most of the models are approximately in the right ballpark. They've got an ENSO. It's about the right sort of strength. It has about the right sort of period. Some have excessively peaked power spectra. Slightly worrying, perhaps, bearing in mind these are factors of 10, so it's a logarithmic y-axis. These models down here basically don't have an ENSO. And that's a little bit of a worry. That, certainly as far as the fourth assessment report, these were state-of-the-art couple climate system models, and most of them do okay, but not every single one. So, if you were going to employ a model to look at ENSO, you probably wouldn't choose either of those two. So continuing my slight worry about ENSO, this is a model intercomparison. This is not strictly evaluation now, this is comparing the models against each other, but I still think it's important as a lesson in humility perhaps. This shows for a mid-range scenario, or mid-range climate change scenario, the change in ENSO variability during the 21st century. And basically you see that half of them have ENSO getting weaker, half of them have ENSO getting stronger. The ones that are actually in bold are the ones which were identified on the previous slide as having the best ENSO, are the ones that agree best with observations. So even selecting the models for the agree best with observations, there's still 3 have ENSO getting weaker, 3 have ENSO getting stronger. Well, that's a bit of a worry. And taking that even further, plotting now, same model, same scenario, this is changed ENSO strength along the y-axis. This is along the x-axis is whether the tropical Pacific gets warmer or colder. Now, you can see now that for a mid-range scenario by 2100, the models don't actually even agree on whether the Pacific will get warmer or colder. And some of the models on the left, like the IPSL model, are amongst those that have the most realistic climate. So I actually have this figure on the wall of my office to remind me that models aren't perfect. And in some ways, arguably, we're still nowhere, at least in terms of some phenomena or understanding or ability to predict some phenomena. So you guys, you've still got challenges ahead of you. Your mission should be to try and get all those points into the same quadrant. And then at least we can agree on the sign of changes. That would be a start. So I thought it might be quite fun to cover the development of a couple of models from the beginning through to the present day, because it will show you how they've evolved and show you what the trends are, which will give us some maybe insights into how we want to push things in the future. So over time, as our understanding has improved, as our computers have got faster and we can actually afford to run more complex models, the models themselves have become more complete. So we started out in the 60s and 70s with atmosphere and ocean models. They generally had some sort of basic representation of the land surface within them. And as we've got better and better at modelling, we've progressively added additional phenomena into the models. So now we have coupling of those two together, for example, rather than running them separately. We have sea ice, and then progressively since the 1990s, we've been starting to incorporate aerosols, descriptions of chemistry, and descriptions of biogeochemistry into the models. So a sort of state-of-the-art model in the 2010s can actually be an extremely comprehensive Earth system model. Now, one of the great things about preparing talks like this is you always learn things yourself. And I went back yesterday actually to try and find what was the earliest paper, what was the first paper published using a fully coupled atmosphere, ocean, general circulation model. And anyone want to hazard a guess as to what year that might have been? The first global coupled model. Well, I was surprised. No one's feeling brave? Okay. I put you out of your misery. I assumed it was probably 1980s, like maybe 85, something like that. You know, actually it was 1969. So amazing. So coupled climate system modeling's been going for about 44 years now. And there's this amazing paper by Suki Manabe and Kirk Bryan. This guy, as you'll learn in the next few minutes, was absolutely the founding father of coupled climate system modelling. For the first 20, 30 years, he was absolutely at the forefront every step of the way. And in fact, the group he founded in the US, the GFDL, is still, even to this day, at the forefront of coupled climate system modelling. Now, I'm struggling to imagine what it would have been like in 1969 to build and run a climate model. And of course, it was very simple, very low resolution. But the thing is, I absolutely love this. This is their model evaluation slide. So they only ran the model for 1 year. I mean, the computers were way too slow. I mean, my phone's probably 1,000 times faster than the computer they were running on. But this shows in the bottom of the ocean, 4 kilometers down. Oops. Down. That'll all make sense in a moment. From the bottom of the ocean to the top of the atmosphere, the zonal mean temperature. And that's the model on the left and observed on the right. And actually, if you look at that, yeah, it's a bit excessively, flat in terms of meridional gradient. But basically, the idea is cold at the bottom of the ocean, it's warm at the top, hottest in the tropics. You've got the right sort of vertical distribution of the atmosphere with a tropopause here. And this really simple low-resolution model ran for just 1 year, basically got the climate system about right. Or in terms of zonal mean, almost as well as a modern day model. So this actually was, this was an amazing paper at the time. This is the first proof of concept. It showed that from first principles, just starting with the basic physical equations, you can write a model, stick it into a computer, run it for a year, and basically the right answer drops out. And at the time, this would have been an absolute revelation. So I think it's really cool. I wanted to actually get some idea of what the computer they were running actually looked like. So I couldn't find a specific computer, but this is a Univac 1108. This is the exact type of machine they ran on. It's not the specific one. And isn't this great? You've got spinning tapes in the background, and there's probably a card deck here. So I'm sure it was all punched cards. There wouldn't be any sort of long-term disk storage. So this was what coupled modelling was like, circa 1969. This is a very stark picture. I also find this promotional image, which I think captures the glamour of climate modelling much more successfully than the previous image. But moving swiftly along, they kept on going. Skip forward to 1991, the first century-long integrations, still being led by Suki Manabe. And this was the first paper to actually look at the longer-term response of the climate system using a coupled climate system model. And again, this wonderful graph that would have been completely unprecedented at the time, showing that as you increase CO2 concentration at 1% per annum, the Earth gradually warms. Faster in the northern hemisphere, slower in the southern hemisphere, as we now know. And the guys kept on going. 1994, so 25 years after they first started, 25 years, think about that, that's a career. 25 years after they first ran for 1 year, now they could finally start running a model for 500 years. And so they ran a series of simulations. They ran a control, 2 times CO2, 4 times CO2. And if you run a simulation now with state-of-the-art model, you get basically the same graph. Exactly the same thing we know, that the Earth warms quickly as you increase the CO2 concentrations, but there's still some thermal inertia built into the system, and even after you've stabilised, it keeps on warming. And the other thing they discovered in this paper that we now know, but at the time, again, was really new, was, like, seeing a really wonky graphic. This is actually what it looked like in the original paper. It was actually wonky, because in these days, there was no computer typesetting. It was all done by scanning or something. So it actually looks that way in the paper. But you have this great graph, and this is the strength of the overturning circulation in the North Atlantic. And they were the first guys to actually show that, for a control, it just sort of boogies along like this. But you double the CO2 concentration, it weakens and weakens and weakens as you're increasing the CO2. And then you sort of let go, as everything stabilises, it recovers. But for a 4 times CO2 simulation, the whole thing shuts down. And so they were kind of showing for the first time that when you can run a climate system for these sorts of timescales and like peer hundreds of years into potential futures, you actually start to get this really interesting behaviour of the climate system exhibiting 2 different stable states. And of course, this paper showing that the overturning circulation shuts down in response to increasing greenhouse gases was 1 decade later filmed. It turned into a movie. But actually that paper was the basis of where the idea came from, that was subsequently developed, that, like I say, 10 years later was entertaining cinema audiences with that wonderfully realistic example of rapid climate change. But by this point, basically by the 1990s, we had the basic physical framework of carbon models down pat. We had the idea of an atmospheric circulation model, ocean circulation model, sea ice, land surface, and that physical core was done by now. So since then, starting from that basic framework, we've been evolving everything further. So now we're starting to put biology and put chemistry into the system. So now we have models that have an interactive carbon cycle. So rather than having just a feeder scenario into your model and just tell your model, look, CO2 is going to do this, now we have Earth system models that can actually simulate. So this is a fairly recent paper from a model with a fully interactive carbon cycle showing that for a 20th century evaluation simulation, black is what the world actually did, green was a control simulation, and these blue and red lines are what the model did. So we have models now that are actually capable of simulating the carbon cycle and how it evolves with a very high degree of accuracy. The other thing we've been doing since those early papers, of course, is really cranking up the spatial resolution. And this is from a recent paper showing 2 different versions of a GFDL model. So GFDL is still, more than 40 years after that Manabi paper, still at the cutting edge of coupled climate system modelling. So this shows 2 different configurations of their model. CM 2.1 is a sort of typical sort of resolution of models that will go into the 5th assessment report. They've got a new version called CM 2.5 that runs at 50 kilometre resolution, and probably can't see that as well as I'd like from back there, but really high resolution model simulation, really capturing some of the finer details of the climate system. And at this point, I just want to jump out and show you a movie I found this week that just completely blew me away, because this shows the sort of tools. Can I move that window? Oh, there we go. Yeah. So this is from a CM 2.6 model, which is even higher than CM 2.5. This is 25K resolution, fully coupled climate system model. I'll just go now. And this is actually a model. This is not observation. This is a model simulation. Ew. It's too big. The models are too big. There we go. So there you go. So this is what absolutely state-of-the-art coupled climate system model. And this shows just evolution of sea surface salinity in the Arctic over a year. Is it actually playing? No, that's okay. That's all right. I did bring another version of the same movie, different format. Nope. Okay. Okay.
The other version should work if you open it with VLC.
Do we have VLC on this video?
Yeah, it's very long.
It doesn't like Valentine's Day.
It just
Stops.
stops in 5 seconds and you can download fully. Yeah, open it on with VLC.
That's if we have VLC. I've got VLC. There it is. Okay. How long have you got?
The very first couple model, what was the resolution?
It was 5 by 5 degrees. So yeah, very coarse. I only had about 5 on it. And it was 5 molecular levels in the atmosphere and 9 in the ocean, something like that. Oh yeah, I forgot to mention that they ran it for 1 year. So you saw that big, like, room-sized mainframe. They're called mainframes then. So at 50 days. On one of those machines, 50 days to run it for 1 year. So they were right at the cutting edge. What we'll do is, okay, here we go. Yay. At last. So I hope it was worth the wait. This is a model. I mean, look at these eddies in here. So I think this is so exciting because these are, if you feel inspired after this week to go away and pursue research careers in coupled climate system modelling, these are the tools. You know, you're not dealing with 5-degree models and mainframes the size of a small building. You're dealing with models that actually have 25 kilometre resolution. Yeah, I love these eddies. Yeah, this is obviously the northern extension of the Gulf Stream coming up around Greenland into the Arctic.
Are there observations that compare to that resolution?
I'm a modeler. Yeah. Anyone know? I'm sure there are satellite observations. Don't ask me about the real world. It's not my area of expertise.
So you could be lying to us.
How can anything so beautiful be wrong? I think on this one, art, yeah, beauty trumps science on this one. There we go at last.
Is that a simulator?
I believe that's just a control simulation. So that's just inherent internal variability within the model. So that's the cutting edge anyway as far as resolution goes. So what sort of future opportunities are there? I mean, apart from 25 kilometre high resolution sort of models? Well, really, I mean, we've got basically the physics of the system done. Chemistry, biology is almost there. So I think the real frontier, as far as coupled climate system modelling goes, is us. The next step is to put us into the models, put human societies, economies, and so on into the model, somehow couple them in. And this isn't just a pipe dream, people were doing this. So here's a diagram from the US, a conceptual model for, conceptual design for a coupled climate system model that incorporates not just everything we've seen, like atmosphere, ocean, land surface, ecosystem, all that stuff, but also includes models of human activity, agriculture, ecosystems. And a model like this, if and when built, won't just give you all the things you know and used to seeing from models like temperature, precipitation, sea level rise, and so on. If it actually works, and that's the if, but will be capable of simulating things like GDP growth, energy use, policy costs, health impacts, agriculture. And that's kind of the dream for modelling as far as many people are concerned. That we're moving beyond atmospheres and oceans and actually seeing humans now as being another Lego block that we bolt onto our model, because we're in the Anthropocene now. Humans are part of the ecosystem. So the next step is to actually simulate the dynamical interactions between economies, societies, and the climate system. Just another example from a paper that just came out in the last few weeks. This is looking at something people are discussing potentially for the 21st century's geoengineering. So this was a paper that actually looked at the human climate system as a coupled system that would iteratively interact via geoengineering to changes in the temperature of the Earth. And actually it's attempted to simulate the behaviour of the entire human climate system dynamically responding to changes in the climate system, which is kind of quite a mind-boggling concept, but certainly this is the cutting edge, and this is where we're going. So, conclusions. Hopefully I've shown you that Kerbal climate system model is able to reproduce the key features of the global climate. As a result, they're incredibly powerful tools, not perfect, but powerful, for exploring the past, present and future of the climate system. However, there's still great potential, as hopefully some of you will explore, to develop the models further. I think partly by increasing resolution, but particularly by incorporating descriptions of additional components of the human climate system. I like to try and remind myself from time to time what a great privilege it is to be a climate system modeler, because once you've got these models that are realistic representations of the world, it actually gives you this ability effectively to create and destroy worlds. Best not to try and get too much of a megalomaniac about that, but you do have that ability, at least fictitious worlds, but nonetheless worlds that are realistic and behave in the same way as the real world. So I think with that power, I think it's very careful to remember to think carefully when designing, building and using your climate system models, because no model is perfect. You've got to be careful not to get carried away by its power and see your models as being perfect. So, as a parting prop, does anyone talk about black boxes this week? This is a black box. Now, what you've got to be really careful to do is to remember your model is not a black box. You can treat your model as a black box if you want to do. You can just run your model, some numbers can pop out the other end, you can publish them as a paper and say this is the answer to the problem. But that's really dangerous. You've got to be careful to actually understand the tools that you're working with. So you need to understand the strengths but also the weaknesses and the limitations of the tools you work with. So what I'm going to demonstrate here is that it's much more satisfying not just to treat models as the black box, but to open up the black box and see what lies within. Pass it around, enjoy. And with that, I'll just wrap up with a quote from the that immortal philosopher Spider-Man. Remember, with great power comes great responsibility. And with that, thank you and enjoy.
Just a very quick one. Did you see how many citations that first paper
actually had? Actually, no. Might not be that many, because I actually hadn't heard of it until this week when I was researching. I think it got eclipsed by later papers that did it better, perhaps. But I don't know. I should Google Scholar and find the answer.